Okay, so everything, well, almost all I'm going to talk about is a joint work, a series of joint articles with Sophie Mourier-Genoux. Okay, I mentioned this. And so the subject, main subject what I'm going to talk is the notion of Q-deformed rational numbers and Q-deformed irrationals. So Q numbers, as we call it with Sophie. And Q, what does it mean, Q? Well, Q deformation is not a theory in mathematics, it's a philosophy. Q analogs, Q deformations are everywhere in the algebra, in geometry, in analysis, everywhere. You remember quantum groups, quantum algebras, quantum calculus, quantum everything. Q is quantum, right? Q is quantum. And indeed, physicists use this notion of Q deformations, quantum groups. Q is a parameter. Well, for physicists, it's maybe not a parameter, a number. It is an exponential of Planck constant, h. Right? But when we study the mathematical part of the story, it turns out that Q actually goes back to Leonhard Euler and other people. So if you open old articles about, so it's called Q series, Q belongs to Euler. It's a kind of contradiction because Max Planck was not born at that time. So why is it quantum? Because Euler used Q for quotient. Quotient. This is how Euler used this. And open just any article about so-called Q series, Rogers, Ramanujan. If you open Rogers' papers, beautiful papers about continued fractions, analytic continued fractions, you will see Q. Q, not X, not Y as a variable. Q. Q is quotient, but in Latin it will be quotum. And then if you are a little bit dumb or whatever, some professional defect, then quantum or quantum, just the same, right? But this is the only explanation I can give you. Otherwise, I don't understand. What? Quantum or quantum? Quantum numbers. So, of course, to be, how to say, to make it nice, we should say quantum. Okay, so now let me go. As I mentioned, there are all sorts of Q deformations. So we are interested in some combinatorial part of the story, numbers. I want Q-deformed numbers, right? And what do we know? Once again, if you open any book on quantum calculus, quantum mechanics, you will see the following expression, and sometimes even index Q is 1 minus Q to the n, 1 minus Q. So it's a very simple polynomial, as everybody can see. This simple cyclotomic polynomial. So this formula goes back to Euler and Gauss. So Euler studied a beautiful function, a product of infinite product of these expressions. One phi of Q is a product of sort of infinite factorial, and it is a wonderful series in Q, formal series in one variable Q, which is in the as a foundation of at least two different series, combinatorics on the one hand and some modular forms on the other hand. So it's a very, very famous object. Now, Gauss used this polynomial to construct more complicated. So Euler, it is 1676 approximately, and Gauss 1808.
Not 17? 17? 1776?
Was I saying Newton? Gauss. What did Gauss suggest? So first of all, we can define factorials, just multiplying these polynomials from 1 to n, and then if we have these factorials, we can try to define Q-deformed binomial, Q binomial or Gaussian binomial, which by definition is given by the same formula that we know, and Q factorial, which is the product of these objects, and then these two factorials. Okay, this is the definition. So this is a Q binomial, and it will be my main example to illustrate the notion of Q analog, of Q deformation. Before I go to the main part of the talk. So, well, first of all, it's a polynomial. It is a polynomial in Q, which is not completely obvious, but easy to prove by induction. You can Q deform the formula of Pascal identity, and you will see by induction. It is a polynomial. It is a polynomial with integer positive coefficients. Positive integer coef. All this is important. Why? Because in combinatorics, positive integer numbers must have some combinatorial meaning. They count something. Okay, so maybe let me give you just one example. The first interesting example is this 6, as you remember. What do you have? Just try to do this exercise. You will get this 2q squared q4. So this is a polynomial we get in this particular example. Okay, so it is somewhat deformed version of 6, right? But it is different from what we have here, right? Of course, because we have this coefficient 2. Also, if you make another exercise, so if you take factorial, you also will get some 3 factorial will give you another polynomial. So there are different ways to Q deform 6, right? Actually, we don't deform 6, we deform infinite sequence of numbers. Here we deform all natural numbers. Here we deform binomials. Also, we can deform factorial. So one individual object cannot be Q deformed. It cannot be deformed. Only infinite sequence of it. One should remember it. So if when we will talk of rational numbers, you cannot Q deform individual rational numbers. It has no meaning. You only can deform all of them together. So you should count them in some way. You choose which way you prefer, and then you could deform the whole sequence. Okay. Now, so the most important is then when you have a Q analog, it should satisfy some properties. Okay. So once again, I will not develop the general theory because otherwise I would stay at least for this second term and give a course of lectures. It's impossible, but I will show you some on this example. With this example of the most classical example of Q binomial, I will show you. So first of all, I don't even say it's not a property. It's a kind of evidence, obvious think that if you put Q equals 1, this means, well, in physics language, we think that H equals 0. You go back to the classical case, so you get back your initial object, right? You specialize at Q equals 1, you get, but this is not the property I want to say. So there are at least 3 properties. First, if some object, combinatorial object, counts something, then the Q analog counts exactly the same things. Same things, but better. It counts better. Why? So let me give you an example. So actually, binomial coefficients count many different things. You will maybe 100 of different things in the image, right? So I give only one example, but it will be true for any example you would consider. So what can we say? So let me take a rectangle of size m by n minus m. Then I consider northeast passes like this. And the number of these passes is what?
M plus m.
Huh?
M plus m.
Yeah, exactly. So this is the number of these northeast path. Okay. Now suppose now that I care how many boxes do we have under the graph of this path. Okay, then actually it will be exactly the uniform coefficient, and the number of boxes or area under the path is the power of exponent of Q. Okay, so it means that every coefficient of our polynomial has combinatorial minimum. It's much stronger than just the number of passes. So we count much the same thing, but with more details. Okay, well, this example, we have, what do we have? We have 2 by 2 rectangle, okay, exactly one pass bound in 0, one pass bound in 1, and 2 which have 2 passes which have exactly 2 boxes underneath. Okay, exactly 2, and this is why the coefficient here is 2. Okay, well, now as I mentioned, there are hundreds of examples you can check, and it is kind of miracle that every time you obtain the same polynomial, the same different problems counted by binomials and the same polynomial. Next, another example. So the second property. Property number B. Okay, so if you open the classical book on enumerative combinatorics by Richard Stanley, in the first volume, at least half of it speaks of Q analogs, actually. And Stanley says that perhaps the most important property that it has count something over finite fields. So it's a geometric property, but in finite geometry over finite field. So I will say geometry over FQ. Okay, and Q is no more formal parameter as it used to be. It's not just a variable here. It's what it is. It's a power of some prime number. Okay, Okay, immediately, this our main example, binomials, is what? Is a number of points in the Grassmannian of m-dimensional subspace in n-dimensional vector space over Fq. Oh, it's a very old classic theorem. Well, by the way, what here it's also a theorem. It's also a theorem. Also an old result. Okay, so not very difficult to prove. It's an easy statement, but it's a classical theorem. And the last, the last requirement in general, so that a Q analog can be called Q analog. The last requirement we want is that it is related to some Q calculus or Q algebra, quantum algebra. Well, so why do we call them binomial coefficients? Because if you take two variables x and y, and you put x plus y to n, then you get m x y. Right? Okay. Well, this is true. So this is a binomial theorem, right? And this is true when this is true, when x and y commute. Suppose now that they don't commute. X, y equals, and you put q somewhere here. Yx is q times xy. So this is, physicists call this algebra quantum plane or Manin plane for Yuri Ivanovich Manin. Okay, then if you suppose this, that what do you get? Theorem. But again, easy to prove by induction, but it is remarkable. So why it is remarkable? Because actually we have the same polynomial here, the same polynomial counting boxes. Okay, here q is formal parameter, here q is the power of prime. Why do we get the same polynomial? Why? Well, so the only answer I know is that because mathematics is kind of miracle. That's no other reason. Okay, so now we are ready. We are ready to study. Actually, they were known until recently, until the coronavirus infections, there were no analog of Q rational numbers. And we will try to do something which will satisfy at least the three requirements I mentioned, but actually we will get much more, many more beautiful properties of it. Definition. So, well, this is, after this long introduction, I can finally start my talk. So, definition. Suppose now we have n over m, okay, a rational number. I will explain what will be the Q analog of it. What is the Q deformation? Okay, and so the first, so of course it's not just the quotient of these two polynomials, because as I said, we cannot deform in an individual object. And here, this is what we want to do if we do that. Okay, so it's not an individual. We must deform them all. And if you don't know how to do this, if you don't know how to define, how to make some meaningful definition, and also if you are geometer by any chance, then you should look for a group of symmetry. You find a group of symmetry which will act on the objects, and then you will ask that the notion you introduce is invariant under this action, commutes with this action, whatever. So okay. So which group of symmetry acting on rational numbers? Well, numbers are the only way to transform. If x is a number, the only way I know it, maybe some can suggest something else, you take a linear fractional transformation. Okay? So, well, if you say x is rational, then you want a, b, c, d, the coefficients belong to be integers here. So every coefficient of this 2 by 2 matrix is integer, and actually the matrix I take is element of SL2Z. Z. So it means the determinant is 1. Why do I want the determinant 1? Because actually we don't see the determinant in the action. I want it to be as efficient as possible. So the simple situation is when the group action is faithful, means there is no kernel. Well, unfortunately, well, not maybe fortunately, there is one kernel. So also, if we take -1 matrix, it will act trivially. Therefore, I put here P SL2Z. P SL2Z, which is just SL2Z quotient by the center, which is plus -1 matrix. Okay? Yeah. Just over the center is a cyclic group of order 2. Okay, so it's quotient by its center, PSL2Z. Okay, well you can forget P if you wish, but then there will be the kernel of this action. Okay, so it acts on rational numbers. True? Almost true. So rational numbers with one extra point, which is infinity. My favorite number, 1 over 0. favorite rational. You should add here. Well, more geometrically speaking, it's a projective line over Q. Okay, this is geometric way to think. Okay, very good. So we have this group action, but what I'm looking for, I want some quantization map from this Q, well, let me put Q bar with this infinity completed to where? Where I would like to have rational functions, okay, in Q. And so, as I say, I have a group G, which is PSL2Z, G, operating here on this projectivized rational line. Okay, so now I need to figure out. It's not yet clear how to define this action on the rational function, and then I will ask that my map, which associate to every rational its kernel, commutes with the action. Now the last effort to make the definition. So the definition, it's not just an obvious thing. Last effort, we need to know how PSL2Z operates on rational functions in one variable. This is known. This is known in the literature. Actually, okay, so my group, I will describe you the action explicitly in terms of the generators. You probably know, most of us know that there are that one can choose two simple generators of PSL2Z. C from translations of this matrix. When I write matrix, it means it up to the sign, okay? Okay, because we take the quotient. And S is sort of inversions, 1 minus 0 minus 1, 1, 0. X goes minus 1 over x. Okay, and here x goes to x plus 1. Now, so these are generators of SL2Z, and this is the way it acts on rationals by linear fraction. Now, what should I have here? Actually, we know what should be the answer on the integers. I don't want to contradict Euler and Gauss. I don't want to contradict the classics. And if you look at this formula, and if you add 1, n plus 1 q, then check, it is n q times n plus 1. Right? It's just obvious from the formula. This means that to define the action of t here on the rational, I need to put q here. Then just apply the formula. Apply the formula. You will get exactly this recurrence. Okay? And this I will call t index q. So this is a deformed q. Now, for S, what should be written for S? The only matrix which will have the same relations with T as before. So you know that to define a group you need generators, T and S, and you need to know the relations. The relations are S squared is TS cubed equals 1. Well, actually, maybe you say minus 1, but we will already take the quotient. Okay, so actually there is only one matrix such that for the deformed matrix, the relations will be the same. So once again, there is some scalar multiple which appear, but it disappears when we take the action. So what we look here is not exactly the matrices, deformed matrices, but deformed operations, where how they. So that's it. Now we have this, and a theorem that we proved with Sophie. It's so dangerous sort of theorem slash definition. So it's a theorem that makes the definition possible. It says that there exists a unique map that I denote this way from Q to Z, Q commuting with SL to Z action, or PSL to Z, but PSL to Z action, okay? And send them, wait, so if it can be not, it will not be unique if we don't know one point. We only need to know one point. Because this action is transitive. I forgot to say, but so the action on the line, of course, is transitive. It means if we know only where one point goes, then the fact that it commutes with the group action will fix the rest. So I want just 0 remains 0. That's it. So 2 requirements. First, it commutes with the action, and then it sends 0 to 0. Then it becomes unique. And this is our definition. So this is what we want to say. Now, I will give you explicit formula. Okay, so this is the how to say, well, theoretical, the conceptual way to define the notion of Q-deformed rationals, but there is an explicit formula for it. Explicit formula. Okay. Formula. So you remember that a rational number can be developed in a infinite, or in a finite continued fraction. Well, it's not precisely unique, but almost unique, this expansion. Okay, so the formula is the first coefficient. I just erased the formula, but you remember. So what Euler and Gauss told us, you put Q analog of this integer. A's are positive integer coefficients. Here we should put Q to the A1. It's also obvious, because if we have, suppose that M equals 1, and so we only develop the numerator, then we don't want it to be different from Euler and Gauss. And now the second is funny. Imagine, because here you should inverse. It's the same formula, but with 1 over q. The coefficient, the parameter is inversed here. And here you put q minus a2, and so on. But then it repeats. Q minus 1 over q minus, so and here, depending on the parity of this last coefficient, or the number of the coefficient. Okay? And here also. This sign, okay? Clear? So now you can use this formula. You can teach your computer very fast to calculate Q numbers. There are many different programs that one can use. Okay. Now I promised you nice properties, and indeed there are analogs of properties A, B, and C. It counts something, E, H. So what do we know? So this n over m, index q, is a quotient of two polynomials, n over q, m over q. Both are polynomials with positive integer coefficients. And there are beautiful statement, beautiful theorem. One belongs to Nick Ovenhouse, young students. So there, some of them were obtained by undergraduate students, by the way. I need to mention, I invite every young people to, you can write this program very easily to calculate the Q numbers. And then all known properties were first obtained by computer experiments, and then it was proved. Okay, so, well, so, but I don't want to give you all these analogs of this A, B, and C. Believe me that we know something, but I will give you extra beautiful properties. First, okay, we call it total positivity. Total positivity. What does this mean? Suppose that we have two rationals, n over m and n prime over m prime. Suppose that this is greater than this, the first than the second. Okay? In which sense can we say that the order is preserved by this Q deformation? Can one say this? Actually, yes, well, we can. So the theorem that we proved with Sophie in our first article on the, it is, so if it says if n over m is greater than n prime over n prime, then the cross product n of q m prime of q, this cross polynomial minus m of q n prime of q, this polynomial has positive integer coefficient. Well, integer is obvious, but it's positive coefficients. Positive. It means that in this sense you can say that the order is preserved. It is very, very important. So it's total positivity. For some combinatorial reasons, it has a meaning of total positivity. Okay, now, even more interesting.
Pardon me.
Yeah.
So I'm assuming we've kept the definition as Q equals e to the h. You mentioned Planck's constant, did you not? Okay, so this ensures that we actually have a reasonable order, because Planck's constant is considered to just be some dimensionless real number.
You should think of it as a parameter. Small h is small parameter, q is parameter close to 1.
Oh,
but
okay.
you see, when I say positive coefficients, it means every power q appears with positive coefficient. Well, so
we're defining it partial order, right? Partial,
yeah,
an order.
yeah. So if q is positive, then you can say that. Of course, it remains. It keeps the order, right? So if q is positive, but if q is complex, then it's difficult. So
Right.
in this formal sense, it is true because you say you care every coefficient. Okay. Well, so but you are right. Indeed, it is important to think that q. What does it mean? Q? Well, no, don't know what. Maybe it is a power of a prime. Maybe it is a small. It is a parameter close to 1, a real parameter. Or maybe it is complex parameter. Or maybe something else. It should make sense in any situation, but the theory becomes different. So, yeah. Okay, second important property. We were not able to prove it with Sophie. We just conjectured, but it was proved by a long sequence of papers of other people, combinatorics. So actually n of q, this is true for both numerator and denominator. This polynomial, it has positive integer coefficient. Actually, it is monic polynomial. It starts from 1, then there is coefficient, first coefficient, second coefficient, and so on. Then it stops with some, again, this coefficient equals 1 at some power q. Yeah, this k depends both of numerator and denominator. And why did I put this coefficient bigger, greater? That's because actually the theorem, it was our conjecture, which is proved now. Theorem states that this sequence of coefficient is unimodal. Unimodal. What does it mean, unimodal? It means what's written here. First it grows monotonously, not strictly monotonous. There can be equal coefficient, but there is no oscillation. You can say greater than, smaller than, again greater. So it's like that small lonely mountain here appears. This is important both for combinatorics and for geometry. Unimodal sequences, as probably you may know, so they appear as a Betti number of any cohomology theory, right? Any known cohomology theory has this property. In combinatorics, it's fundamental, this unimodal. By the way, in our favorite example of q binomial coefficients, this polynomial has this property. The sequence of its coefficients is unimodal, and it is celebrated theorem. So the unimodality, it is celebrated theorem of Sylvester, who proved a conjecture of Arthur Cayley that was unproved for 20 years, and Sylvester gave a proof. So now there are many different proofs which are known, but all of them are non-trivial. So it's a celebrated theorem, unimodality for the binomial coefficient. So here we also have this property, unimodality. Well, and the last property I mentioned today, because there are many other beautiful properties, but the last...
Before you mention it, I'm supposed to warn you.
Yeah,
I'm supposed to warn you 7 minutes.
This is the last thing I mentioned. You can probably check, you can plug things. Yeah, it is property number 3 in my list. It's called stabilization. Stabilization phenomenon. What does it mean? So suppose now x is irrational. I actually, we didn't understand this fast with Sophie, but it's our second paper on the subject I'm trying to tell you. So suppose that it's irrational. I gave a countable number of talks about Q rationals, and every time someone would ask, well, what about a Q rational? Can you tell us what should be a Q analog quantum version of irrational number. And I was inevitably answered, I cannot tell you, because suppose, okay, what should be reasonable to say? Okay, if x is an irrational, then we can find many different sequences of rationals convergent to x. So these are rational numbers. Okay. Well, for the rational numbers, I do know what is a Q deformation. I tried to explain it now. Okay. But in which sense this sequence would converge to something? It was not clear at all, because when I will give you examples. Why it doesn't work?
We tested it.
It always works before, but it doesn't. Okay, now, in which sense it will converge? If I take you, I will show you, hopefully, sequences of rational functions, and you will see that the coefficients grow in uncontrollable way. So it's difficult to say what, but actually it does. It does. What we should do is that you should consider the Taylor expansion, Taylor series at 0, at q equals 0. And it turns out that miraculously there is a convergence. So the theorem states the following. So if we develop this rational function as a Taylor series, so this n, for every n, I have a sequence of rational functions. For every n, I have a rational function. I develop it into a Taylor series, and it turns out that the series will stabilize when n goes to infinity. So the stabilize. This series will stabilize when n tends to infinity. Well, and this is a remarkable property. It stabilizes. So is this, and this allows us to define what is a Q analog of an irrational number. This stabilized series. So analog of Q irrational number will be a Taylor series, a series in Q with integer coefficients. And this is what I hope to do. Well, and this is a remarkable property. If you don't make the definition as we did, you just naively take the quotient of two polynomials, cyclotomic polynomials corresponding to numerator and denominator, you will never get this stabilization phenomena. Okay, so this is the main property of this Q rationals. And as a bonus of all this, I will mention you another beautiful property. There are plenty of them for Q rational numbers. One of them is relation to Jones polynomials, for instance. So there is a class of nodes, which is called rational nodes, which is numbered by rational numbers. It's a theory that goes back to John Conway. So n over n, every rational number corresponds to some rational node. Okay, and it turns out that the most beautiful, perhaps, invariant of this node, which is called Jones polynomial, can be calculated in terms of the numerator and denominator of our Q rationals. Actually, well, the theorem says the following, that this Jones polynomial up to some normalization, which I will not maybe explain in the detail, it is the combination Q times numerator plus 1 minus Q denominator. Okay, so this is an interesting property, which another interesting property, which also relates us to some part of knot theory, is that the group actions that I...
Wait, I don't understand. You're defining the left-hand side by the right-hand side?
Yeah, well, so this is the Jones.
Oh, the traditional.
The traditional, the classical, that was defined approximately in 1985. So by Vaughan Jones. So this is a Jones polynomial, which is an invariant, important invariant of a node. So if we restrict it to the rational nodes, which are parameterized by rational numbers, then what we have? We have this combination. Actually, so well, we have 2 times more invariance, of course, because we have numerator and denominator. But if we combine them in this way, so what we get is the Jones. Jones polynomial is given by this formula. Why? Okay, that was one of the first points. We started, actually, our motivation with Sophie to study this kind of things was not just to abstract deform, Q-deform rationals, it was to understand the Jones polynomials in terms of some cluster algebra variables, and this is what led us to this formula. So that was maybe the first result. The first result. Then we realized that actually what we have here, numerator and denominator, it's both of them altogether allow us to define this Q rational. So maybe one last thing I wanted to mention. Okay, let us think about the irrationals. Well, so many things are already known for rational numbers, Q rational numbers, and the literature became substantial. But Q irrationals remain kind of terra incognita, almost. But we have some observations. We have some observations about irrationals. So the first thing one can ask is, can we say something about the radius of convergence? Now, okay, I say so far Q is a formal parameter, but suppose that Q is a complex number. Do we know it is convergent series or divergent series or what? And so, well, we have a conjecture and we have a theorem. The conjecture says the following, that the radius of convergence is always greater, for every x, the radius of convergence is greater or equal to 3 minus square root of 5 over 2. This specific number, actually, this we know, it's not a conjecture, so this is precisely the radius of convergence of this series if we take the golden ratio. Radius of x equals 1 plus square root of 5 over 2. So if we take this golden ratio or any other number projectively equivalent to this, so PSL to Z equivalent to this x, then what we get? This is a convergence. And it turns out that for any other irrational number, the radius of convergence will be actually greater. This is a computer experimentations that tells us it's actually better than a proof, because you know that a proof is true right until the first counterexample. Right? But when the computer doesn't lie, so we know this is true for every x which is not equivalent to the golden ratio. The radius will be greater, so it is equal only for a golden ratio or equivalent number. And so this conjecture, if a conjecture can be analog of a classical theorem, then this conjecture is the analog of the famous Hurwitz theorem that tells us that the golden ratio is the most irrational number. It's the worst approximable by rationals. This is exactly what happens here. So this the worst situation. So, but even for it, we already have it is approximately 0.38. So it is the radius of convergence. Well, and the theorem that we proved with Sophie and with Alexander Veselov, our colleague from England, from Loughborough, the theorem says that actually the radius of convergence is always greater or equal to 0.17. So we have a uniform bundle for the radius of convergence, and this is important. So in the neighborhood of 0, in the vicinity of 0, all these formal series converge, and this is important. And so we deduced a corollary. So this allowed us to deduce a corollary. We solved a question recently formulated by John Bierman about the specialization of Burau representation of the braid group B3. So I just mentioned it, but with no detail because we don't have enough time. But so this at least we are getting some corollaries of this theory. Okay, this is perhaps the first application of this theory of Q-deformed numbers to the rest of mathematics. So we hope that there will be many different applications. So there are some attempts to do this, which are projects in progress, but so far at least we have one application. Okay, and this is the end of my talk. Thank you.
Questions from the speaker?
I have one. Can you do continued fractions with these things? Does that definition coincide with the sequence version of the irrational numbers?
Yeah, so yes, thank you for the question. Yes, absolutely. Yes, you remember I gave the implicit formula for Feynman continued fraction. Continued fraction corresponds to rational numbers. But if you expand an irrational number as a continued fraction the same way, and then you apply exactly the same formula, it will converge. This is a part of the theorem of, about the convergence of series. So it is true. Yes, yes. The answer is yeah.
So how do I say it? So when Ramanujan sent letters to Hardy, he had these formulas of big continued fractions with really interesting e to some I pi square root of 167 numbers. Yeah. Maybe, like, have you tried putting those in instead of the golden ratio?
We did, yeah, because actually, if you take this famous Rogers-Ramanujan continued fraction, at this point, Ramanujan rediscovered some results of Rogers, older, which were actually already known for 20 years before. But well, anyway, so we could discover much more about the continued fraction. But if you put the variable which Rogers also developed, denoted by Q equals 1, then you get the golden ratio. What they did, they also Q deformed the golden ratio, but their Q deformation is different. Well, unfortunately, we cannot get anything. We would be happy to have Rogers-Ramanujan in this example, but what they get satisfies cubic equation. So the continued fraction, the series which represents this Rogers-Ramanujan continued fraction, satisfies cubic equation. We have a quadratic equation here, so it's a more simple way to Q-deform equation. So, but some of the formulas are very, very similar. So there is something in it, but not exactly. This is an interesting question, but this time it's different. This time is different.
Okay, thank you.
Okay.
So at this point, have we abstracted away any usefulness to quantum physics?
Also a very good question. There is one first tentative to do this. So there is Q-deformed Virasoro algebra related to the, well, it's a sophisticated infinite dimensional real algebra that Charlie knows very well, Virasoro. And there is a new version of Q-deformed Virasoro related to this. So it is a work in progress of a young researcher from Lyon, Alexander Thomas. Hopefully will soon be on the archive. So, well, there are first attempt to do this, but not a serious theory yet. But of course, it's in the program. Thank you.
Do you know if this Jones polynomial
Yes.
result has similarities to the Jones polynomial arising from other quantum mathematics, like from UQSL2?
Oh, yes. Well, of course, the Jones polynomial is related to many different things. This is our hope also to connect these Q numbers to various fields. For instance, any relation to quantum group it's not known yet. We don't know. We have no relation yet. Hopefully we will do. So it's a good point. Jones polynomial, well, we need at least some how to say, some points to rely at, to try to attract some, to connect to some other theories. And Jones polynomials is a very promising point to do, but we don't know much yet. There is also a relation to the Alexander polynomial, which I didn't mention, but so some work should be done.
Finite fields?
Sorry?
Finite fields?
Oh yeah, finite fields, it is known. Yes. There is a beautiful theorem of Nicolas Obenhaus, who is a postdoc in Yale. He proved the following. So if you take the Q rational like that, then this polynomial can be interpreted with the following way. So we just create, we create something which is called snake graph. And we do it the following way. So we take the coefficient of the continued fraction, A1, so we take A1 boxes here. Then we add A2 boxes in the other direction. Then we take A3, we put A3 boxes here, and so on. Okay? So this is why it's called the snake graph. It is like that of this form, how snake crawls on the blackboard, right? And then, so it is composed of these boxes. After that, Nick says the following. It's very similar of what we see for the binomial, Q binomials, but instead of the rectangle, we have this snake graph. Then after that, we do this exactly the same thing. We study this north-east path that fit into the snake graph, and he says so. It defines some Young diagram, and then this Young diagram will correspond to some Schubert cell in some Grassmannian with the correctly chosen parameters. Okay, and the collection of points over FQ of this Grassmannian will exactly give us the numerator. This is the theorem of Owenhaus. Really beautiful. And to get the same is true for the denominator, but we should the snake graph should be started from A2 instead of A1. That's it. So this is the only difference. So this is a, how to say, geometric meaning of a finite field of this. Maybe there are other statements, but this is what is known. Thank you.
Further questions? So let's thank the speaker again.